Okay, welcome to the video for our final section on quadratic equations and functions. And what we're looking at today is applications of quadratic functions. And so now we're going to get examples of the real life use of the quadratic functions, and we're going to have to graph, find x-intercepts and y-intercepts, maximums, possibly minimums, and we're going to have to interpret those in the context of what the problem is talking about. Okay, so what we're going to do for this video is I'm going to take you through example 1. So I'll explain that, show what you need to do on the calculator, and answer the questions with you. And then for example 2, I'll record answers in the second part of the video, but that's going to be the one that you're going to attempt on your own. Okay, so let's start with example number 1. We'll just read through here quickly. So NASA creates a weightless environment by flying a plane in a series of parabolic paths. So of course we're talking about parabolas, which are quadratic functions. The height in feet of a plane after t seconds in a parabolic flight path can be modeled by the graph h of t. So remember, this is just function notation. H of t is essentially, if you think of your calculator, the y. So y equals, only this time we are talking about h of t because it's height with respect to time. So the height of the plane is a function of time. And then you see our equation here, minus 11t squared plus 700t plus 21,000 is an equation with t as the variable. The idea being, if we substituted in different t values, different times, we would get the height of the plane as the answer when we substituted in the different values. Okay, so what we're going to do is, for part A, we have to sketch and label a graph of the h of t function on the given axes, and we're going to find and label the vertex and the y-intercept, and we're going to label the axes of the graph as well. And so down here is where we're going to have the graph. What we would do over here is we would write down t. The x-axis is time. In this case, it would be h of t, which is the height of the plane with respect to time. Okay, we are using the calculator for this, and so I'm going to actually do the sketch on the calculator, and then I'll copy that over at a later stage. Okay, so first things first, what I'm going to do is go onto the home page. I'm going to start a new document, and I need a graphs document in this case. I'm going to type in my function, and so minus 11x squared. Remember, there is a t on here, but you don't use that. The calculator is not programmed to treat that as a variable, and so we must use x, y, and z are the only three possibilities. So I'm going to express it in terms of x. So minus 11x squared plus 700x plus 21,000. So the first thing I do, of course, I'm going to hit enter, and you don't see anything at all. And hopefully what you recognized or realized was that when you entered this, the graph has got a y-intercept, a starting value of 21,000. And so when you look at your graph, naturally, with our graph going from minus 6 to 6 approximately, we're definitely not going to be able to see this graph. So lots of different options. The most efficient, of course, is to go into the window. The problem here is if we zoom out, we may have to zoom out multiple times. You do have a zoom fit option where the calculator will try and set a window for you that is appropriate. So that's not a bad place to start. And of course, the alternative is to, so I'm going to go in here, and I'm going to just use the window setting and set it myself. Okay, in this case, x is, remember, the t-axis, so this represents time. We're not going to have any negative time, so I'm going to leave in a minus 2, even though we can't have negative time, just so that we can see the axes. Not exactly sure how long the plane is going to fly for, so I'm just going to start off by putting in 30, and we'll see later I might need to adjust that. So I've got a graph that goes from negative time, really, so including 0 all the way up to 30 seconds. My y minimum, I'm going to leave in a negative value again, just because I want to make sure I can still see the x-axis. And then my y maximum, I know that the graph starts at 21,000, so I'm going to put in 50,000 and we'll see if that is in fact big enough. So I click OK. Now I have an idea of what my graph looks like, but I can't see it completely in a parabolic shape. And so what I want to do is go back into the window a second time. And this time what I'm going to do is increase the x. I'm going to move that to 100. My maximum does appear to be, or my y max does appear to be high enough. So we'll increase that, and now we have a slightly clearer picture of the function, starting over here and peaking well under the 50,000, and so 100 was enough in terms of time. So in the context of this, everything's happening within the first 100 seconds of the parabolic flight path. Okay, so we've done the first part. We now need to do some labels. We were asked for the vertex and the y-intercept. So if I come back over here, for the vertex, we're going to use the analyze graph, and what we want is a maximum. So I'm going to go to the left and a point to the right, and here we have our maximum, 31.818 and 32.136. We'll interpret those in a little bit. To get my y-intercept, what I'm going to do is use the trace function. So I'm going to trace the graph, and I'll use the cursors and go to the left. It might take a little while because my increments are relatively small. We'll trace along here. And what I'm of course looking for is the y-intercept. You should know from the previous lesson, of course, that the y-intercept that I'm looking for is going to be at 21,000. And what I'm going to do then is just grab the graph and just drag it back to make sure that I can see the other key parts of the graph. Okay, so we've taken care of the first one. We've graphed the function, we've labeled the vertex and the y-intercept. Okay, now part B, we need to find the maximum height that the plane reaches and at what time, after how many seconds does it reach this. Hopefully what you realize from this is actually something that we've just found. The vertex can give me the answer to both of these questions. The vertex is the point at which the graph turns. It is the maximum. And so the x value in this case, if you recall, represents time. The y value represents height. And so what we have here is a maximum height of 32,136 feet. And that occurs after 31.818 seconds. So at what time? After 31.818 seconds. What is the maximum height? And there we have 32,136. Okay. The passengers experience a weightless environment when the height of the plane is greater than or equal to 30,800 feet. Okay, so once again, what you can see here is you've been given a height. And essentially what that means is you've been given a y equals value, or in the context of our example, an h of t value. And so I'm going to go back to my graph over here, and what I'm going to do is sketch another graph, and so I'm going to push tab, and what I'm going to graph is 30,800, and it's going to produce a horizontal line for me. And what I'm interested in finding in this case, so let me move that out of the way, is the coordinates of the intersection between those two graphs, because that will show when they're equal. And if you come back to the question, you'll see you are weightless anytime the height of the plane is greater than or equal to. And so essentially from the point of intersection until the second point of intersection will give you the times between which the passengers are weightless. So to find an intersection, we're going to use analyze graph, and we're after number 4, the intersection. Go to the left of the first intersection point, go to the right, there's our first one. We're going to do that again. Analyze graph, intersection to the left and to the right, and there we have our second intersection point. We're going to have to just reshuffle some stuff here, getting a little bit crowded over there, and we'll just move that function name over there. Okay, and so we have the y values are the given height, 30,800 of course, and the two times indicate the intersection points where those are equal, and we are of course interested in all times between 20.8 seconds and 42.8 seconds. And so let's come back over here, and we're going to just write down the answers to that. And so just clean this up a little bit. So between 20.80 and 42.84, correct to 2 decimal places, and of course I'm using or equals to because that's what the information in the question said. Okay, scrolling down, for how long do the passengers experience weightlessness? So that hopefully as you think this through, you'll understand that what we need to do there is take 42.84, subtract 20.8, and that will give us the period of time for which they are weightless, and so that's going to give us 22.04 seconds that they were weightless for. Coming down here, of course this is one of the key application questions. What does the y-intercept value represent? So of course the y-intercept in our case occurs at 0, 21,000, and so if you pay careful attention to what each of these represent, 0 represents time, 21,000 represents h of t, which is the height in feet, and so at time 0 the height is 21,000, and so the answer, what does the y-intercept represent? The answer is it represents the starting height of the plane. Now of course we know that the plane has to start on the ground, it can't start 21,000 feet in the air, so interpreting that in the context of the problem, it represents the height at which the parabolic flight path of the plane starts. Okay, so that is the starting height, our starting height, and then we could fill in for the parabolic flight path. Okay, I'm going to leave that for now in the interest of time. And the last thing we need to answer is what is the domain and range. Typically, if we're talking about an algebraic function, the answer is going to be slightly different to this. The idea here is that we are attempting to provide a real-life example, and so we need to adhere to certain constraints. First of all, we can see from the graph we already calculated the maximum, and so in terms of the range, so normally we do domain first, in terms of the range, this parabola opens down, and so its h of t is going to be less than or equal to 32,136, because that was the maximum that it reached. But what you should hopefully recognize, of course, is that this is an aeroplane, and what we don't want is to have any negative heights, because that would imply that it's flown into and through the ground. And so the range is from 0 up to 32,136. Similarly, for the domain, which of course in the context of this problem is representing time, you cannot have negative time, and so t is going to be greater than 0, but in the context of this, less than or equal to, and now we need to come back to our graph, and we are looking at the point at which the plane touches down at the ground, on the ground again. And so very quickly I'm going to find my 0 of the blue graph over here. So there's my lower bound and my upper bound, and the 0 occurs at 85.87 seconds, and so 85.87, and that gives you your domain. Okay, go ahead and do the second example, and you can watch the second part of the video.